Sound check. Good morning. Sound check. Good morning.
These same ejections that are coming out as quasars in the low and the minor axis come out in the disk of the galaxy, and they drag the material out with it, and they form these sort of flux tubes in which there's some material, ionized material of the galaxy, which then is constrained, or maybe even there's pinch activity, and they form these characteristic young stars along the galaxy spiral arms. And so what I'm trying to say is I think there's a unified phenomenon here of ejection from these nuclei, forming quasars, new galaxies out this way, and pulling out material of the old galaxy, forming these new stars and so forth. And that I would suggest this as a sort of a mechanism for understanding galaxies, evolution of galaxies, birth of galaxies, and so forth.
I very clearly remember, though, about 5 years ago when I was reading on the internet and discovered the electric universe theory. And this brought it all back to me. This brought back the joy of science and exploration. It was no longer the science of the advanced mathematics that no one brought it all back to me. This brought back the joy of science and exploration. Else can understand. Instead, it brought it back to the science that creates this modern world. It's the electromagnetism that we know about in our motors and generators and oscillators, transmitters, receivers. All the things that have created our modern world are incorporated into the electric universe theory.
When Newton devised his laws of motion, it was in the gaslight, horse and buggy era, and electricity had not been discovered yet. So it's really puzzling that when we found out about electricity, that the theory did not get modified. That is hard for me to understand, especially because they haven't really explained themselves why. But here's the thing. Had Newton known about electricity, do you think that he would have incorporated it? The galaxy has long magnetic field lines that cocoon a quasar. It is shot from the galaxy core, the plasmoid of the galaxy core. Eventually, it breaks out, which sounds familiar with Earth and Saturn and the Herbig Haro. A lot of cocoons in space. Anyway, it begins to gain atoms. Now they've got all this glorified kerfluffles that have no bearing to reality. Who wants reality, right? Better to close our eyes and imagine gigantic nothingness. As long as we can use words like black hole, quantum, time travel, string theory, inflation, dark this and dark that. What's worse is most people buy it. Just go look at a mainstream cosmology video. The views are in the millions, and it doesn't take long. People are interested, but we're like the backwater. They gotta stumble over us until they find the truth. And like Winston Churchill said about the truth, man, we're lucky to get 100,000. What is wrong with this picture? Meanwhile, over half the population feels lost with no direction. Doctors treat them with chemicals. Everything about man is warped, backwards, upside down. We haven't changed much really at all since the catastrophe. But it's not the people. It is the mainframe is defunct. I've loved science all my life, but I was skeptical of many things, especially in cosmology, my favorite subject. And when you find out about something that was done that was wrong, like the way Halton Arp was treated, how can you ignore that? How can a compassionate human being ignore that? But what is just as bad, if not worse, is how could his discovery and or results be ignored? That is contrary to the whole scientific method. I mean, these people are professional scientists, and look how they act. They act like they're sorority brothers. And, this is our side because we have this belief and that's your side. And if you have that belief, then we don't like you. We don't want you to be a part of our little group. And if you do want to be a part of our group, you have to pay attention to the hierarchy. And you can only study this or that, but you cannot go out of these bounds. That's not science. That's high school drama. It has no place in the world of discovery. And that's what gives me the passion to want to try to help it get back on the right track. And I think the biggest thing that bothers me about science, and just about every other area of discovery, we seem to want to make it about the messenger and not the message. Why is that? Why does it matter who makes a discovery? If he makes the discovery and you want to give him his propers for that, then fine. But they make it all about that. I have to say that I take my hat off to people who can put the time in to get a PhD. Like Einstein says, it's the imagination that is a sign of high intelligence, not book knowledge. It's pretty bad when you can pull their guru out on him, on things he says, and then use it against them. It doesn't say a lot for them, but they turn on him like a rabid viper the first time it doesn't agree with them. There's a couple different kinds of smart. There's book smart, there's street smart, and then there's just experience smart, which goes with the street smarts.
There's an old saying, to the victors belong the spoils.
There's another old saying, Senator. Don't piss down my back and tell me it's raining.
Because we're all counting on it, whether we know it or not. I knew something was wrong. Even in the late 90s, early 2000s, there was a dysfunction. I knew that black holes were a mathematical theory, or the way stars and galaxies work. That's just mankind's attempt to put a label on it, because we love to put labels on things. It's too hard for them to say we don't know. I don't want to come off as being grandiose. I just want to say that, I care. That's why we're here. We care. And by the looks of things, a lot of you agree with me. We find what's being offered to us unacceptable. Because we're smart enough to know that you can't just throw out some disprovable thing and expect us to embrace it and think it's the truth. To me, science is looking for the truth, looking for empirical evidence and nothing more, and going where the facts lead you. It's the only way you're going to learn. If you invent pink elephants, what does that really do for you? Nothing. It just comes up with a fancy word that people can say to sound smart. Mathematics, to me, can help you gain an aspect of something like, for example, how to orbit a planet. Yeah, but to put life on a chalkboard with numbers, it's like apples and oranges to me. Just using common sense can get you by. But as it said, common sense ain't too common. I'd like for it to just go back to good old astronomy. Instead of having 16 different kinds of astronomers and tell the mathematicians to find another job, find other work. They've really screwed things up. The word physicist to me anymore means bullshit artist. What good has come from them? Tell me. of Cepheid variable stars in the Great Nebula. The Andromeda constellation proved existence of galaxies outside the Milky Way. Astronomers have determined the shape of the Milky Way by using radio waves because they penetrate the interstellar gas and dust without being scattered or absorbed. Other galaxies were first believed to be nebula or star clusters within the Milky Way. 6 times 10 to the 11th power times the mass of our sun.
There we go.
Galaxies and the universe. Other galaxies were first believed to be nebula or star clusters within the Milky Way, but Edwin Hubble's discovery of Cepheid variable stars in the Great Nebula, Andromeda constellation, proved existence of galaxies outside the Milky Way. Astronomers have determined the shape of the Milky Way by using radio waves because they penetrate the interstellar gas and dust without being scattered or absorbed. Other galaxies were first believed to be nebula or star clusters within the Milky Way. 6 times 10 to the 11th power times the mass of our sun is the mass of the Milky Way. Standard model studies claim to provide evidence that there is a great amount of unseen matter called dark matter composed of dim stellar remnants that have mass. The Milky Way is a barred spiral galaxy that is 100,000 light years across. Part of it is visible on a clear night from Earth as a thick band of stars stretching across the sky. The closest galaxy to the Milky Way is the Andromeda Galaxy, or M31, and it is 2.3 million light years away. Types of galaxies. Elliptical galaxies. This is an elliptical galaxy. Galaxies that are not flattened into disks do not have spiral arms. Their shapes range from round ellipticals to elongated elliptical. A possible elliptical galaxy is Virgo A. Elliptical galaxies contain anywhere from tens of millions to 100 trillion stars that travel in irregular orbits. Also known as M87, Virgo A is a supergiant elliptical galaxy in the constellation of Virgo, one of the most massive galaxies in the local universe. It has a jet of energetic plasma that originates at the core and extends at least 1,500 parsecs.
Coordinates are down in the lower right. Distances will be shown in the lower left.
Spiral galaxy. This is a spiral galaxy. Galaxies with spiral arms consisting of interstellar matter and young star clusters. The bulge consists of old stellar population. There are normal and barred spirals. A possible example of a spiral galaxy would be the Sombrero Galaxy, which is also in the Virgo constellation. It is 31,100,000 light years from Earth. Its size is 49,000 light years. It's about half the size of the Milky Way galaxy. It's larger and more massive than previously thought, indicative of a giant elliptical galaxy. Galaxy has a magnitude of 8 points.
Distance along the equator between 15 degrees of longitude. Wait, this is 15. Sorry about that. Wait a minute. No, wait a minute. Oh, that's 15 degrees latitude. Sorry. Yeah, I got it right. I know what that should look like. All right, so that's distance is around 16,000 kilometers, just rounding off, 1634. So let's look at a distance at latitude 45 between between 15 degrees. 15 degrees is right there. Jeez, my eyes are going bad. So that's 1151. Let's see what that distance looks like south of the equator here. $11.76. All right, so there's going to be discrepancies in the tens of kilometers only because of where I point and click, and also, you know, how true is the TIFF image in up, down, and side to side. So you can only get this to be so close. But I hope that this demonstration will let people understand that the fact that this map appears to be very distorted at the ends, which it is, because the further away you go from where you are projecting, right? The further away you go, you're going to increase distortion with this type of a projection, the azimuthal equidistant projection. So, you know, you just can't lay a ruler on here and expect the distances to make any sense. You've got to have the math behind it, which is the math used to create the projection. So that's what I wanted to show you, is that even though I'll show you another distance here, let's say at latitude 60, let's do that. So we'll go from 0 longitude to 15 degrees west. And, you know, I'm not zoomed. Maybe I should zoom in there. Let me try zooming in. Try to pick it as close as I possibly can. All right, so back to the measure. So there's 0 longitude. We'll go west 15 degrees, and we're on the you can see 60 right here. This is the 60th parallel north. So right about there, we're looking at 838 kilometers. All right. Now I'm going to go south of the equator at 60 degrees south, and we'll measure the same thing. Let's go down here. Zoom in. There's 75. That's 75 south. So here's 60. So we're going to measure. Am I on the right latitude? No, I'm not. Back out a little bit. Oh, here's 60. Okay, I was not on the right latitude. There we go. And there we go. So now we're on the correct latitude, 60. South 60, going from 0 degrees longitude to 15 degrees longitude west. I got about 837. So as you can see, the distance is correct. The visual appearance is, you know, larger on this type of a map. All right, so got to be aware of that. So you couldn't, I don't even think that the scale would help you. I've been looking at this map for a while thinking, how would I even use the scale? Trying to, if you wanted to try to use a ruler, you'd have to figure out how to use these scales. You got two scales. But I don't know. I don't think you could literally use a ruler on this map. But it works really well when you apply the coordinate values to the pixels. Now, there was a request for some distances between some cities, and I hope I can see them on here. Ray wanted the distance from someplace in Australia to someplace in South America. Was it Sydney to Santiago? I think that's the flight Max Egan takes. There's New Zealand. That's Sydney there. All right, so there's Sydney, and let me go find Santiago. Then we'll measure that distance. You're seeing it live. I've not done this before. All right. Oh boy. All right, that's Falkland Islands, Buenos Aires. I don't know if it's marked on here. I don't even. Let me go find. Let's see here. Dun, 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 dun. So I made this video before. Flat Earth map works perfectly. It got some strange. I think I threw people off. Some people didn't want to hear that the map works perfectly, but it does. It works for its purpose, you know. Here we go. Ray. No, that's not it. Here. Oh, Sydney, Santiago. That's what he wants to know. Well, let's see here. I think Santiago's in Chile, right? Chile. Okay. Okay, well. I don't see that Santiago is labeled. Let me get a visual on where it might be. All right, so at least I can tell you, like, maybe I can just measure a distance to something near the middle of Chile. So it's not way down here. It's going to be more northward. Let's look up there. Oh, there's, okay. It looks like Santiago's gone. They tore it off the map. So it appears that Santiago is in between this town and, or it's near to this town, Valparaiso. All right, so it's probably like right here. Okay, so that's what we're going to use. I'm going to go from there. Boom. I'm going to zoom out. Okay, I'm just going to hover here where it says Sydney. I don't see a dot representing Sydney, but I'll just go like right there. Boom, Sydney. And it says that it's 11,293 kilometers. So, I mean, I'm going to say plus or minus 500 kilometers just because I couldn't say for sure where I should be clicking here. But you notice that that thing is curved. Well, the reason it's curved is because it's measuring a great circle distance on the globe being represented by this flattened map. You know, maps are flat. It's just so simple, and there's so much arguing about all this. And you just got to recognize the fact that maps are flat and the Earth is not. Just study maps. I mean, if you think the Earth is flat and that it's being hidden from you, then do a little research. You know, stop watching flat Earth videos and maybe do a little research into map making, the history of mapping. I post stuff like that in my Facebook group, Flat Earth Can't Geodesy. In fact, let's go look at my recent post. I'm going to come back to Global Mapper in just a minute. I don't have this, nothing is planned today. I'm just playing. This is my Saturday morning little playtime. I haven't looked at the chat yet. Sorry. I'm just kind of focusing in on what I want to do right now. I'll take a look a little bit later. Welcome, 2 more members. Discussion. See where I posted this. It's just recent. This is a really calm group. There's no name calling anymore. Nothing. It's very specific what we do in here. We look at actual information, and I encourage people to discuss, present your information. I'll be getting to this FE core at some point. I wish I had more time to do these things because it's fun, but I'll be getting to the FE core at some point. It's, we definitely went over it a little bit in here. Let's see. I just want to show you a recent post. y'all see me? I did my instrument. I calibrated it through the water, so that my instrument wasn't being fooled by that arrow switching through the medium. This is important technical process there. You can take a look at that video. It's on my channel. Dun, dun, dun. Here it is. This one here. So I'm just asking the question, if the Earth is flat, and when flat earthers get together to decide on how they will make their new map of the flat Earth, what methods and equipment will they use to measure the world and plot all the detailed features? Will they invent new instruments and new procedures, or use the same ones that were used for many centuries to produce all the maps we use today? And I'm just suggesting search on, quote, history of measuring and mapping the world. And, you'll come up with tons and tons of information. So I'm just suggesting to you that it's just like, how does this work? As the pinned post, as I say in the pinned post, that all the distances and elevations and locations are now and always have been determined by surveyors, making the measurements and producing the maps to plot those locations. And the appeal I hear from flat earthers is for us to return to the basic fundamentals we can trust in order to make evaluations to reach conclusions. I have no problem with that. Go ahead and do that. Research where the maps come from. And, when you hear someone starting to talk like this, yeah, but they were all Masons and they what? What? Show us what they did with these maps. How are these maps wrong? Do they not work? Can you find your way from your house to your friend's house in another state? Are you using maps? Are these maps working? Come on, get real. So do the real research. And it should include how maps are made. Now I'm going to go back to, how maps are made through the centuries and how they're made today. Take a look, What I want to do next is reproject this. We'll see what happens to it. I'll turn the measure button off. So let's see. Right now it is projected. Let's look at the configuration. Right now I have it centered on the North Pole at the central latitude is 90. And I used -90 for, that is west 90, just so that the map would appear up and down, just as it's shown here in the TIFF image. All right. Now, what if we flip it over? All right. I've done this before and it worked. So I'm going to do it live and let's see what happens. It's thinking about it. All right, boom. All right, now we're looking at the exact same piece of paper, and we just flipped it over. And here's the that little paper tab, that is hooked to the rivet. There's the rivet all elongated. But look what we see here. I mean, it just looks like what you would expect to see if you flip the globe over. Just trying to zoom in. All right, so it looks like Antarctica to me. I mean, it may not be exact because I can't vouch for the representation of the detail on the edge there. But, I mean, it looks decent. It looks like maps you've seen before. So, okay, we just took the Gleason map flipped it over, and we're looking at it from the South Pole now. Let's see. What else can we do? I'm going to do a couple things. I'm going to put it at, I'm going to put this map at, I'm going to center it on Philadelphia, or close to New Jersey, you know, like Jersey, Philly area, right? Well, I guess we could either leave it as a azimuthal equidistant map. Okay, we'll do that just so we could see what does this type. Look at all these different projections, by the way. You know, we have a whole history of really smart people trying to figure out the best way to represent a three-dimensional globe that would work well for their region, their country, their area. So there's a lot of different projections that can be used, okay? All right, so we're going to stick with the azimuthal equidistant. And I'm going to come over here to Jersey. I'm going to say minus, I'll just go with 75. And we'll put it up there at about 40 degrees latitude. Okay? See what happens. You're seeing it live. All right, so let's go. You know, it's almost like you're taking a globe and kind of spinning it around, right? And obviously, the further you go away from the center of where you've chosen to project from, the more distorted and crazy it's going to look. But I bet you these distances still work because the math behind it is operational when you click and measure distances. But if I come into close to where I've centered the projection, the azimuthal equidistant projection works well within reason in that location, close to it. You know, this, you do not have as much distortion here as you do on the outer edges. So the whole point to that type of projection is that it's you know, it's useful for its intended purpose. The guy made a some type of a time sun device, and that's the projection he chose, so that he could see the whole world in, you know, on one. It was actually more of a device than a you know, than a map itself. I mean, it has a map involved, but he had these two strips that were used somehow. I've not really looked deeply into it, but you could see that it's more of like a device used for navigation, I guess. Okay, so you know, I have some other. I'm going to close this. Unload all. Wait, no, but wait, I'm going to save this. I like this version. Yeah, I'm going to just go ahead and save it. So I'm going to say, let's see. I've got a few of these, as you can see. I know I have one on New Jersey. Today's date, 5/19. I'll say not hungry. Save that. Now I'm going to unload it and open. Here's New Zealand. of an older version. Well, I'm getting hungry for breakfast. There it is, centered on New Zealand. I think I'll also show you some of the other projections I tried it on. I did the just the Mercator projection. Blah, blah. I think I showed this one too in the other video I did called Flat Earth Map Works Perfectly. And you know, you've seen this map before. This is the one where the lines of latitude are straight across the page. Lines of longitude are straight up and down. Well, what's that going to do? Well, it's going to probably work pretty well in this area, right? But you know, Greenland is not that big. So we all recognize that maps will distort. Maps cause distortion. They do. So the whole thing about using map projections is to choose one that works for your purpose, what you're intending to do, and how you want to represent a region. So you're going to select a projection that works well for your area, and you try to minimize the distortion. But there's going to be distortion. There's no doubt about it. In fact, let me go back to Flat Earth Kent Geodesy Facebook group, and I posted a recent thing that I saw discussing the new state plane coordinate systems that we're going to have when we get the new datum. There's a new datum adjustment coming up in 2020 or 22 or thereabouts. Thanks, James. I'm glad you like my group. Here's Chris doing his incredible AutoCAD work. He's a good guy in AutoCAD. He could give Dr. Zach a run for his money. Okay, here. Yeah, I posted this. Here's the United States, and by the way, you know, all the nations have zoned or gridded national grid systems for use in that region for doing surveying. You know, for doing the layout of highways and infrastructure like electrical transmission lines and gas pipelines and whatnot. You know. You're covering large regions. You have to have some way of doing that. So in the United States, we have the U.S. state plane coordinate systems, and depending upon what the direction you're trying to cover, there's basically two mapping projections that are used. These are conformal mapping projections designed to try to minimize the distortion on shape. And so the thing that gives, the giving thing is the distance. So the lengths are where most of the distortion will happen. And we work around that by using grid scale factors. So distances that are measured at ground are reduced to sea level, let's say. It's really to the ellipsoid, but we put it to a common surface, okay? And then from there, it's projected to the mapping grid. And so there's two kinds. There's the conical one, which is the Lambert system. Like Texas is broken up into several zones of using a cone. And go take a look at that. Do a little research on conformal mapping projections. You know, I'm not going to pull it up here, but you can do that. And it's only because you're interested. That's why. And then for the northern for going north-south, what's used is what's called a transverse Mercator projection, and it makes use of a cylinder. So we take a cylinder, intersect it to the Earth in a secant manner to minimize the distortion across that zone. And then you just cut this, you project all the features onto the cylinder, cut the cylinder open like a toilet paper roll, and flatten it out. Boom, you got a map. So, and then up in Alaska, there is one unique zone that uses the oblique Mercator projection. But so for the most part, all the United States are covered by these types of mapping projections. And here's the link to the discussion on what's coming. I haven't read this yet. I downloaded it yesterday and I'm going to read it. But it goes through the whole history of the datums previous, the datums current, and future datums. I just kind of looked through this. I already kind of know what these discussions are about, but it's good information. So there. Let's see, is there anything else I want to do in Global Mapper? That was the main point of this morning's little live hangout. Probably not. Let me get some ideas. Maybe I'll go see the chat. Where is it? Oh, let's see. I guess I'm up too early. Yeah, you're right. It was under the scrape part there. Homestar. Morning, y'all. All right. I guess that's about it. Probably after I shut this down, I'll think of something else to do, but I'll be back. I'll do some more. Did someone just chime in with something? No. Okay. All right. We'll say good morning. Have a great day. I want to do some video on the FE core. I want to come back. I've got a list of things to do. But yeah. Take care, Homestar. I'll be back. Have a good one. See ya.